Priyanka. Today we are going to solve a problem on slider crank mechanism for velocity diagram and acceleration diagram. In this video we are going to understand in which direction we have to draw velocity diagram and acceleration diagram when the rotation in clockwise direction or anti-clockwise direction is given. We are also going to understand how to define the direction of angular velocity and angular acceleration from the velocity diagram and acceleration diagram for any link. So please watch this video till end, and we are also going to follow the step-by-step procedure. So please note down that procedure in your notebook. Now first I will read what is the given problem. The crank of a slider crank mechanism rotates clockwise at a constant speed of 300 rpm. The crank is 150 mm and connecting rod is 600 mm long. Determine linear velocity and acceleration of the midpoint of the connecting rod, angular velocity and angular acceleration of the connecting rod at a crank angle of 45 degree from the inner dead center position. So this was the given question. Now we have to first draw the space diagram with some suitable scale. So if we observe, the crank OB is rotating in clockwise direction and it is at angle of 45 degree from inner dead center position. So here if we observe, this is the fixed point O and we have to draw here OB at a degree of 45 degrees. So here is the inner dead center and at other side here is the outer dead center. So from the inner dead center we have to take here the angle 45 degree. We have to also show rotation is in the clockwise direction. Now we have to define some scale. So here we will use scale 1:half. Now the length of this crank OB is given 150 mm. That means we can say here it is 15 cm. So 15 cm, but our scale is 1:half. That means we have to take here the distance equal to 7.5 cm from this point O to B. And in this way point B is getting fixed. Now for the connecting rod, distance is given 600 mm and which is equal to 60 cm. But here as per the scale 1:half we have to take 30 cm. So in the compass we are going to take here B as a center and we will mark here one R at a distance of 30 cm. Now here we have to mark here the point. So from the fixed point O we have to draw one line. And this is the line passing through the center O. That's why we are going to draw this line in the form of dash and dot. So we have to take B as a center and we have to mark here one R on this horizontal line. And this point of intersection will be the point A, and at this end of the connecting rod slider is getting attached. So here is the slider. So we can say that in this diagram the crank OB is rotating in clockwise direction. And here is the slider is having reciprocating motion along this horizontal line and which is passing through the fixed point O. Now we will draw velocity diagram. So before that we will first find out what is the linear velocity of this crank OB. So here the rotational speed of this crank OB is given. So here O is the fixed point and point B is rotating about point O. So here we can say that the end of this B about O, that is NBO, is equal to 300 rpm. So from that we can find out what is the angular velocity omega. So omega BO is equal to 2 pi n by 60, that is equal to 31.42 radians per second. And then from this omega we can find out the linear velocity. So linear velocity V is equal to this distance OB multiplied by omega. So here OB is we have to take into meters. So 0.15 multiplied by 31.42 which is equal to 4.713 meter per second. So when we multiply this term with 1000 we will get the answer in millimeter per second, that is 4713 millimeter per second. So this is the magnitude. So magnitude of velocity of point B about O. So VBO, we can say that VBO. So here O is the fixed point, so simply we can say VB. So VB is equal to this. Now how to show its a direction? So we know that the direction is in the perpendicular direction to the link. So this is the linear velocity and here is the link. Now the rotation is given in clockwise direction. So here is the direction, that is the clockwise direction. So in this direction or towards this direction we have to draw one perpendicular line for the link OB. So here I will use this protractor. So these two edges are perpendicular to each other. So I will align one edge to this link OB and I will draw for the other edge one perpendicular line but passing through this point P. So here is the VB. So this is the direction of VB. Now we will take one scale to draw this velocity diagram. So I will use here scale for 1000 millimeter per second 5 centimeter scale. So our magnitude for this VB is 4713. So if I write here 4713 millimeter per second, what is the scale that we have to take? So here we will make cross multiplication, that is 4713 multiplied by 5 divided by 1000, that is equal to 23.56. So this is the magnitude that we have to take. I will write here 23.56 centimeter. Now if we observe this diagram, here is the fixed point O. So I will select one particular point, that is the point O. Now I have to take the line parallel to this VB and we have to take scale 23.56. So I will use here roller. With the help of roller I will take the line parallel to this VB. So 23.56. So here I have to take, I will use here 23.5 approximately. So here is the point. So initial point is O and final point is B. So I will show arrow from O towards B and this vector OB will indicate the velocity of B. So I will write here VB. Now we will move for the next. So next link is BA. So here also we don't know where is the direction, but we know that the velocity is always in perpendicular direction to this link BA. So here the initial point is B and final point is A. So I will write here velocity of A with respect to B, that is VAB, and I have to take the line perpendicular to this link BA. So how to take this perpendicular line? So I will use this protractor. So I will align one edge with this link BA and from the other edge I will draw here one construction line, that is the perpendicular line. So here initial point is B and final point is A. So I will draw here the line parallel to this perpendicular line, that is the construction line. Now here exact location of this point A is unknown, but we know that initial point is B and final point is A. So I will show arrow in the downward direction. Now if we observe here is the slider at this point A and this slider is getting reciprocating motion along this horizontal line and this line is passing through the fixed point O. So we have to show this direction of motion as it is in the velocity diagram, because this reciprocating motion we will transfer here as it is and it will be passing through this point O. So we have to draw one horizontal line but passing through this point O. So here also O is initial point and A is the final point. So I will show arrow here from O towards A. So here is the point of intersection and this point of intersection is A. So how we can define this vector OA? That is the velocity of A with respect to O. So here O is the fixed point, so simply we can say VA. Now how we can define this vector BA? So here velocity of A with respect to B. So I will define diagram is getting completed. Now the main important thing is that how we can define the direction. So direction of this link BA, how we can define this. So I will use here the compass, and here is the perpendicular line. So this perpendicular line is facing towards the downward direction. So I will show that. So this is the rough construction. So this is for only the understanding purpose. So this is the perpendicular line. So we don't know where is the direction is upward or downward, but if we observe here is the downward direction. So if I take this downward direction, then this is the direction of velocity of this point A with respect to B. So here B is the center point and this is the direction of the velocity. So if I take here the compass, take B as a center and move the compass in the downward direction. So here is the direction. So if I draw here, then this is the anti-clockwise direction. So we can say that the omega for omega AB is having anti-clockwise direction about center B. So it is important point here about center B, because we have to move the compass by taking the center as a B and in the direction to the direction of this velocity. Now we will calculate magnitude of velocity AB. So for that we have to measure the length of this vector BA. So if we measure, it is equal to 16 centimeter. So as per this scale, 1000 millimeter per second is equal to 5 centimeter. So suppose if I write here 16 centimeter, then here is the question mark. So here we have to make cross multiplication, that is 16 into 1000 divided by 5, and which is equal to 3200 millimeter per second and which is equal to 3.2 meter per second. So this is the velocity AB, and here is the direction, that is we can say that omega AB is having direction that is in the anti-clockwise direction. Now we will move for the next, that is how we can define here the velocity of A with respect to point O. So if we observe, here is the velocity of A with respect to point O, that is shown with this horizontal line, and the direction of this velocity of A is towards the right hand side direction. So we can say that here during this reciprocating motion, when the crank OB is moving in the clockwise direction, then this slider A is moving in this forward direction, because we have to use here the same arrow, and this is arrow used for the linear velocity of A. So how we can define its magnitude? So for that we have to measure this vector OA, and it is having length 23 centimeter. So by using this scale we can convert it into 4600 millimeter per second, which is equal to 4.6 meter per second. Then again there is the question is that we have to select the midpoint of this crank AB, and here is the point D, and we have to find out the velocity at this point D. So how we can define this? So if we observe, here is the AB is having midpoint D. So I will say that AB divided by AD. So or I will say that AB divided by BD, which is equal to, in velocity diagram here is also vector AB. So I will say that AB divided by BD, that is I have to take this. Now if we observe, we know what is the total length AB, that is given 600 millimeter, that means here 60 centimeter divided by BD. So D is the midpoint, so BD is 30 centimeter, which is equal to, now this AB. So this vector AB is having 16 centimeter. So I will write here as a 16 divided by BD. So BD is unknown. So here if we calculate this BD, then it is also equal to 16 by 2, that is 8 centimeter. So we have to select here BD distance, that is 8 centimeter, and here we have to locate this point D. So in velocity diagram we will use here the small letter, so here is the D. So how we can decide or how we can define the velocity at this point D? So O is the fixed point about which this crank is getting rotated, and this crank is having the connection with this link BA over which there is the point D. So I have to join this point D to the point O. So if I join this, then here is the fixed point O. So I will show here the arrow towards the point D. That is, initial point is O and final point is D, and this will indicate us the velocity of this point D. So if I measure the length of vector OD, it is 21.6 centimeter. So we have to convert it, that is 4320 millimeter per second, and which is equal to 4.32 meter per second. So this is the answer. Now we will move to draw the acceleration diagram with some suitable scale. So before that, we have to understand any acceleration is having two components. First one is the radial component and second one is the tangential component. So how to calculate that? So suppose if we consider xy is a particular length, then this xy, that is the radial component of acceleration, we have to show a raised to r xy, and which is equal to linear velocity square for this link divided by length of the link. So this is the formula to calculate the radial component, and it is parallel to the link xy. So here this is the formula to calculate the magnitude, and here it is parallel to the link, that is, this is the direction. Now in the same way, what is the formula to calculate the tangential component of acceleration? So here we have to show a raised to t xy is equal to alpha, that is the angular acceleration alpha of that link, that is alpha xy multiplied by the length of link xy. So this is, from this we can calculate the magnitude of this tangential component of acceleration, and how we can define the direction. So it is perpendicular to the link xy. So if we observe, radial component is parallel to the link xy, tangential component is perpendicular to link xy. So we can say that this radial component and tangential component are perpendicular to each other. So first, as per the data, now we know what is the linear velocity of this crank. Then we also know what is the linear velocity of this connecting rod BA. So from this linear velocity we can calculate the radial component. But what about the tangential component? So here, when the crank is getting rotated with constant speed, then there is no any tangential component for this crank. And here in this question, the angular acceleration alpha is not mentioned. So when it is not mentioned, then we have to take for a crank, that is tangential component is equal to 0. So here in this question, we are going to consider that this crank is getting rotated along a constant rotational speed. So we are going to consider only here the radial component for this crank OB. So how to calculate that? So we will define it that a raised to r BO is equal to, now what is the value of velocity for this VB? That is 4.713. So 4.713 square divided by length. So length we have to take in meter, that is 0.15, which is equal to 148.08 meter per second square. Now in the same way we have to calculate the radial component of this link BA. So here a raised to r AB. So what is the linear velocity of this AB? That is 3.2 meter per second. So 3.2 square divided by length. So length we have to take in meter, that is 0.6. So which is equal to 17.06 meter per second square. So now here this radial component we will consider here as a BO, or simply we can say AB, because for this crank there is no any tangential component. Now before starting to draw the acceleration diagram, we have to remember one rule, that in which direction we have to draw this acceleration diagram. So first, what is the first step? That we have to select one point and which indicates the fixed point. So in this diagram, fixed point is O. So in acceleration diagram we will consider these points, that is O, B, A, etc. as a O dash, B dash, A dash. So I will consider here as a fixed point as a O dash. Now in which direction we have to draw the radial component, because it is parallel to the link xy. So remember that here the fixed point is O and the point B is getting rotated in clockwise direction. So we have to draw the line in the downward direction, that is towards the fixed point. So here in this direction we have to draw the parallel line. So if I take this roller, then I have to take the line parallel to this. So here in this direction I have to draw the line. Now what is the magnitude? So for that we will refer one scale. So here scale 1 meter per second square is equal to 1 by 6 centimeter. So what is the magnitude here for this BO? So it is 148.08 meter per second square. So we will consider here as a 148.1. So if I take 148.1 divided by 6, so it is equal to 24.68. So I have to take scale that is equal to 24.68. So I will mention here 24.68 centimeter that we have to take. So in the same direction, that is arrow, we have to take towards the fixed point or the point about which crank is getting rotated. So I will take the line parallel to here and magnitude 24.6. This is the end point. So now this is initial point is O dash, final point is B dash. And here arrow we have to show, and this arrow indicates us acceleration of this point about O. So I will simply say AB. Because here no any tangential component, so this ARBO we will consider as a AB. Now the next is link AB. So if we observe here radial component for this AB, that is the radial component of this point A about center B. So we know that this radial component is parallel to this link AB. So I will use the red marker for this radial and tangential components because these are the components. So now I have to draw one line parallel to this link AB. So I will draw one line parallel to this link AB but passing through this point B. So here I will draw. Now which direction that we have to take, because on both sides we can draw this line. So I will draw this line on both sides of B. Now which direction that we have to select? So here that is the acceleration of this A about B. So A about B. So here B is the center. So we have to take the arrow towards this point B. So towards the right hand side that we have to show the arrow. That is we have to select this side. Now what is the magnitude that we have to take? So with this scale 1 is to 1 by 6. That is here 17.06 divided by 6. 2.84. So I have to take here 2.8 centimeter. So I will take the distance that is equal to 2.8 and I will select one point. So this point will be B dash to B double dash. I will refer here as a B double dash, and this vector B dash to B double dash will indicate us value of ARAB. So I will write here ARAB. Now how we can define the tangential component for this AB? So radial component and tangential components are perpendicular to each other. So I will take here this protractor and I will align one edge to the B dash B double dash, and from the second edge I will draw here one line in the form of dash. So now we don't know what is the exact magnitude for this tangential component. So we will keep here as it is. Now we will move for the next. Now again there is the acceleration, or we can say there is the motion of this slider. So this motion is the reciprocating motion, and this horizontal line is passing through the point O. So we know that here the velocity is towards the right hand side direction that we have seen in the velocity diagram. So in the same direction I have to draw one horizontal line but passing through the point O. So here is the point O dash. So I will draw here one line that is the parallel to the motion of the slider. So slider is at point A. So I will draw here one horizontal line, and we have to show the same direction, that is, this is the motion of this slider A. So here is the point of intersection. So this point of intersection will be point A. So I will show in the acceleration diagram as a dash. So this is the end point. So here this B double dash to A dash is the represents us the tangential component of acceleration. So I will show arrow in this upward direction, and I will show here A raised to T AB. Now if I join here this A dash and B dash, that is the end point of this radial component and tangential component, then I will get the total acceleration. So I will use here the black marker. So remember that we have to use red markers for only radial component and tangential component. Now we will move for the calculation part, but before that we have to plot the point D, which is the midpoint of this link AB. So here is also A dash B dash that we have connected. So we have to select the midpoint and this point as a D dash. So how to find out the acceleration of this point D with respect to fixed point O? So for that we have to join this point A dash and D dash. So if we measure what is the length of this vector O dash D dash, which is equal to 20 centimeter. So here is the scale, that is 1 meter per second square is equal to 1 by 6 centimeter. So if I write here as a for 20 centimeter, what is the value for acceleration? So here is the question mark. So 20 multiplied by 1 divided by 1 by 6. So which is equal to 120 meter per second square. So this is the magnitude for this acceleration at this point D. Then the next is we have to find out the angular acceleration of AB. So here is the formula, that is for any link angular acceleration alpha. For that we have to require the tangential component of acceleration and length of that link. So first we have to find out what is the tangential component of this AB. So here is the vector A dash to B double dash. So we have to measure the length of this vector A dash to B double dash, and which is equal to 16.5 centimeter. So as per this scale 16.5 centimeter, if we multiply here 16.5 multiplied by 1 divided by 1 by 6, then we will get here 99 meter per second square. So this is the tangential acceleration. So if we put the value in this formula, then 99, which is equal to alpha AB multiplied by length of AB. So length of AB is 0.6 meter. So when we calculate this, we will get alpha AB is equal to 165 radians per second square. So this is the magnitude for the angular acceleration alpha. Now most important thing is that how to define the direction for this alpha. So if we observe here for the radial component, we have taken for this link AB, direction is towards the point B. So I will show here, this is the direction of the radial component, that is the same direction of B dash to B double dash. Now what is the direction of the tangential component? So it is in the perpendicular direction to this link AB. So I will draw here one line that is in the perpendicular direction, and direction is shown in the upward direction. So its direction, so this direction is from point A towards B. So I will use the compass to decide the direction. So if I take A as a center and move the compass in the direction of this tangential component, that is in the upward direction, here the rotation is in anti-clockwise direction. So we can say that this alpha AB is having anti-clockwise rotation about A. So this center that we have to write, so anti-clockwise direction about center A. Or we can also write the clockwise rotation about B. So these two endpoints, so suppose A is the center, then there is the anti-clockwise direction, and suppose we take B as a center, then we have to take the opposite direction, that is the clockwise direction about B. So any one answer that we can write here, and in this way we have to decide the direction for this alpha.